Thanks again for having me here. I will talk about our company, Cortical.io, and about the technology behind what we do. So we are located in Vienna, Austria, which is maybe a little bit unusual, but it's a nice place to be, and we happened to start our business there. As we are working in machine learning in general, specializing on understanding the meaning of text, which is a very fundamental problem to general IT, I would say, we have a slightly different approach, as you will see. And here I just want to put one major distinction, is that we are not so much looking into a trial and error approach, which is very often the way you do things with machine learning. You get an algorithm, you get the parameters, you get your features, you train the whole thing and you look how well it works. And if you want to improve it, you start all over again. We have a different approach because we try to have a solid theory. So we want to have a theoretical framework, or we created a theoretical framework in the first place, which allows us to have a quite concise preview on how well the technology will actually perform on a practical problem. So what is the problem? So let's start at the very beginning. Processing is typically the processing of numbers. It's very straightforward. You can take a number, you can apply an operator, and you get a result. Problem is, if the data is actually something like that, it's cat. Yeah? So what's the value of cat? And there has been a lot of work in this field. Back to the years in the 80s, for example, in the beginning of the second wave of AI. But since then, we have switched to another strategy, which is statistical modeling. And we went on to actually find new ways of generating algorithms. And we forgot that for some data, it's also very interesting to ask, how can I represent the data in the first place? And here on the example of language, I will show that if you choose a smart way of representing text data or language data, things can be much easier than you would imagine in the first place. So the reason we are doing this is we've been working with traditional text processing, natural language processing, information retrieval algorithms for many years. And there are a couple of problems that you have a very hard time to work around. So most of the models, I mean, I put them all in a basket here. They're very different if you look on a more detailed level. But what they all have together is that they are statistical models. They end up being something like brute force calculation because it's a combinatorial problem. You have to try all the combinations until you find the correct one. And what we want to find is a way to actually take the language as it comes in, to take text and to literally compute with the text as it comes in. The problems that we want to overcome is, first of all, a very fundamental problem with statistical models in general. To become a statistical model, it has to be simplified. So, for example, for language, you have to filter out so-called stop words, you have to reduce words to their morphological stem, and so on. A human wouldn't understand that kind of language, so we are losing something, and as we are losing something, we are introducing noise. Then it's, of course, also quite hard to scale because language is an open system. There is an endless number of combinations of words that you can try to find. So as you get more in deep regions of semantics, things become horribly computationally intense to realize. Then, of course, with the more modern approaches, deep learning applied to language, for example, we have the problem of the black box. So you might apply a machine learning algorithm to some text problem. You might even be successful in solving it to some degree, but it's very hard to figure out why it works. And even worse, if it doesn't work, it's even harder to find out why it's not working. So something that's straightforward in general software development, which is debugging, trying to focus on an error, is nearly impossible by looking at a neural network and trying to figure out where's the value that's wrong. And then, of course, you have things like robustness. Yeah? So this famous case where a system is supposed to give you back a truck, for example, a system that is robust could return a concept like car. So it's not actually a truck, but it makes sense to some degree. A statistical model, we call this fallout of the cluster. So you have these basically clouds of cluster data. And if you actually fall out of that cluster, instead of telling you truck or even car, it tells you banana, because what's out there is just unrelated to what is in the center of the cluster. So the problem we want to solve is the fact that if you want to apply natural language processing in a commercial context, it's very risky, it's very expensive, you never know how long it takes to actually come up with a solution. And it's very often unreliable. So if you look closely, you will see, although there are a lot of sort of machine learning applications out there in business, the number of machine learning applications that actually work in a commercial context is very limited. Okay, so the alternative. We are basically trying to come up with a conceptual framework, a theory, on how text data should be processed, or language data. And the reference implementation for understanding text is in fact the human brain. So we were looking for a reasonable, good way of sort of representing what the brain is actually doing with information in general. And we came across a scientist in California called Jeff Hawkins, who created a very solid theory on how the processing of information in general in the human brain happens. And what we did is we said, okay, if Jeff is right with his theory, whatever we could be possibly doing with language has to fall into the constraints of his theory, because language data is just another type of data that we work with. So this theory, basically, I don't go in detail here. There is a lot of literature out there. There's this book on intelligence. If you haven't read it, you really should. It's not technical. It has a lot of insights. So basically, what he says is, what sort of the main message of his theory is that all of your brain is doing always the same thing all over. Yeah? So there is one algorithm that is implemented on your neocortex. That's basically the newest part of the brain that is doing the actual thinking. And regardless if the brain is processing visual information, auditorial information, the whole processing of the data is always the same. It always uses the same algorithm in doing this. The second thing is that there is only one data format. So again, regardless if the data is coming from the visual nerve, from the auditorial nerve, when it reaches the neocortex, it has the same data format, which is called a sparse distributed representation. So sparse means only very few of the features are actually activated. In that case, they are binary features. Neurons can just be sort of activated or non-activated to some degree. So it's a binary structure, it's very sparse, and it's very large. And so we said, okay, however we do it, what we need to find is a way of transforming text that comes in into a sparse distributed representation. And what is special about this representation is that every single bit that you see, so every dot here on the graphical rendering, corresponds to something real. So we do not process information in a statistical manner in our head. Everything we think of and everything we think with relates to something real. And therefore, any representation that the brain could possibly create has to be built on top of something that has been perceived earlier, which is real, therefore. So we have created a way to transform any input text into such a sparse distributed representation. And because it's so hard to say, we call it a semantic fingerprint. And here you see in an overview why we do this. So you have in the first line 3 terms like mobile, iPhone, and smartphone. And hopefully you can see that those 3 fingerprints are to some degree similar. They are similar in the sense as if you put one on top of the other, you will find a majority of the set bits in this representation to overlap. And overlap, in fact, is the key term when it comes to the brain. So everything we do when we think is that we take some data through our sensory organs, we render it in a semantic fingerprint, and we map it to memories that we have stored earlier. And if we have a large overlap, we say, okay, I understand. And if we don't have a large overlap, we say, oh, I have new information here that I need to store. And as you can see in the lower line, you have truck, automobile, and car. And again, they have some sort of reasonable amount of dots that actually overlap, while they are not very similar to the line of mobile, iPhone, and smartphone. So where we want to go with this is that the representation for a word should resemble its meaning. So 2 words that mean similar things should end up looking similar as semantic fingerprints. So the theory that we developed that basically systematically is able to learn semantics from a reference, a pool of reference information, and then to apply what it has learned there to interpret and represent any piece of language. We call it semantic folding, and I will basically explain why it's called like that. Oops. So here, just as an illustration that what I'm showing here is not fully theoretical. Actually, recent real neural research has shown that there is something consistent in this whole approach. So the experiment that was done by Tom Mitchell in Carnegie Mellon was basically to have people exposed to words or concepts via images. And while they were exposed to these concepts, they were put into an fMRI, which is basically a scanner that records the activity of the human neocortex. And so for every word, they could measure which areas of the brain, and so these are pictures of whole brains, if you see them from the top. And the more red you see, the more active a certain area is. And the interesting thing is that if they exposed a person to a word and a day later they exposed that person to the same word, they came up with more or less the same pattern. So what they did is they trained a machine learning system to actually go the other way around, to take an image and to guess what could have been the word that the individual was perceiving. And they realized that they are far beyond 90% of precision in actually guessing the right word. And to start to be a little bit more scary, the funny thing they found out is that they could train this system on the images of person A, and they could still correctly interpret the pictures generated by a person B. Which means that not only are we consistent in how we represent concepts in our head, but we are also consistent across individuals, which of course makes sense because otherwise we were incapable of building societies, talking to each other, and sharing concepts. So some even later research in 2016 showed that they were able at the MIT to actually, so these are neocortices that are unfolded and flattened out. That's why they look so funny. And what they could do is actually show that about 900 something terms could clearly be discriminated just based on fMRI pictures. So they created sort of a dictionary of that. Okay, so this is just to sort of make the argument that we are not just theoretical, but there is some relatedness to biology here. So the way how we actually train our system, because as a human has to be trained by going to school, to university, until you have learned a certain semantics of whatever is relevant, for example, for your job, we have to train the system also. But the big difference here is that we apply this machine learning approach only once in the beginning before we actually use the system. So let's assume that we take some reference material let's say we take a couple of 100,000 pages from Wikipedia because we want to teach the system to understand general English. And what we do is we simply extract the text, and in a second step, we cut the text that we get into little snippets with the goal of having about one context, one major meaning per snippet. A snippet ends up being typically 2-3 sentences. So we extract a couple of million snippets from the reference material. So again, I keep talking about Wikipedia, but it could be anything. So if you take textbooks on medicine, you would teach the system to understand medical English, for example. What we now do with, let's say, the 5 million snippets that we extracted from the reference collection is that we apply a machine learning, an unsupervised machine learning mechanism, so there is no need for tagging or preparing the data by any means. And the system starts to distribute the text over a certain two-dimensional space, namely the space that you have seen in the fingerprints earlier. So that space happens to be 128 times 128 pixels, could be any other size. We have found out that that is a very useful dimension. And we now distribute all the snippets that we have extracted in a way that snippets containing common words, so two snippets sharing a certain number of words, they stay rather close to each other on the map, and snippets that are very different, they stay more far apart. And that basically gives us a topology, a map of the semantics that we have extracted from the training material in the first place. So that's, by the way, the only machine learning step in the whole process. The second part of the generation process, again, which is done before we actually use the system, is that we extract all the terms from our reference collection. And for each of the terms, so here, for example, the term Socrates, I ask now, which are the snippets that contain the term Socrates? And as those snippets have been distributed according to a topology that was computed independently, we get now a distributed activation pattern, if you want, of all the snippets containing the actual word. And we do this for all the words that occur in the training set. So we end up with a fingerprint that represents the overall semantics that have been captured in the semantic map, and the map is folded into the representation of every single atom, which is a word. So I mean, by formulation that might sound complicated, but what you see here is actually what happens. It's as simple as that. And we end up with a fingerprint for each of the terms, and as you can see, terms like the or is have a very high entropy, so they are very evenly distributed. There is very little semantics within this single word. And words like classical Athenian philosopher, they are very structured, if you want, which is an indication for containing a lot of semantic information about them. So now with our dictionary, we can actually train the dictionary on any kind of data. We have even taken the English Wikipedia and other Wikipedias in other languages, and we found that there is a way of algorithmically aligning the topologies between the languages, which leaves us with different systems in different languages, and the fact that a single concept like philosophy, for example, regardless of the language, it always ends up in being the same fingerprint, which means that we can actually take an English word and a French word, and we can directly compare them without needing any sort of translation in the whole thing. And as you can see, it even works with, for example, Chinese, which is a very different structured language. So it's actually independent of the language, but it mostly is dependent of the semantics that you want to capture and represent. So here, for example, you see why we do this. We have the fingerprint for the English word organ, and as you know, that's a typical ambiguous term. So an organ can be a musical instrument, and therefore you see certain clusters that if you actually dive into the cluster, and I told you in the beginning that every single bit is some real information, and as we have trained this on words, the information behind the bits are actually contextual terms. We get clusters in the representation at some region where we get contextual terms like composer, baroque, music, and so on. Another cluster that typically comes together, we get all sorts of musical instruments. And then you have a big cluster over there where you have contexts coming from biology, anatomy. So the interesting thing here is that every word simultaneously shows all the different senses by which it is sort of brought to existence. So you can look at a word and see all the possible meanings in one view, so to say, because it has this two-dimensional structure and different contexts are situated next to each other instead of top of each other. In the next step, because we just don't want to work with words, we want to work with larger structures, we take advantage of the fact that the whole representation is a sparse vector. So it would lead too far here to explain why, but basically it has been demonstrated that sparse vectors can be added together without actually losing information. So you can take, like here, for example, 6 fingerprints, you stack them, you add all the bits that you find in a resulting fingerprint, and you don't lose any information of the individual partial fingerprints. And by doing so, we basically get now a fingerprint that represents the semantic content of the whole sentence. And just as an illustration, you remember organ had this cluster about liver and anatomical things, which you can see here in the first word. And if you look at the resulting fingerprint, it has disappeared. Why has it disappeared? Because no other term actually strengthened that area for the addition, and so it was cut away, which basically shows us that by having to build sentences, we intuitively, so to say, disambiguate any term. And that is done without any extra effort, and therefore it works out sort of effortlessly for us humans to disambiguate language. So why we do this is because we have one major sort of operation that we try to do with those fingerprints, and that's in fact overlapping them and measuring how many bits are shared between 2 fingerprints. So here, for example, a system that has been trained on financial English, on banking and investments and things like that. And that system was capable to see that the expression done deal and the expression signed contract had in fact 30% overlap. Whereas if you change one term, you see the overlap immediately drop. And the interesting thing is that you don't get just a quantitative measure on how similar 2 terms are, but you can also look where the overlap happens, and you look behind the features and you find out what the context is. So here we see that in the upper line, they are similar, mostly in contexts like investors, liquidity, shareholders, and so on. Which means by comparing fingerprints, you get a quantitative measure and you get a qualitative measure in the same time. So we use this basic functionality for a small number of primitives that are like Lego bricks to solve actual business problems. So one is, for example, the computational disambiguation. So if we want to find out what contexts are contained or represented by a certain fingerprint, like here liver, we can ask the system, show me the word with the most similar, with the biggest overlap with my given word. So I get back the word liver. Then I say, okay, I take away all the liver dots from my organ fingerprint, and I ask the system again, what is now the most similar term? And I get back piano, then I take away the piano dots, and I get back church, and so on, until I have no more pixels left in my original representation. And I can do this with any word, with any paragraph, sentence, fingerprint, however it was created. We can sort of decompose it into all its generating contexts. The second one is to actually give back terms based on a query term. So for example, if we query the system with the term Socrates and we say, I want to have associative nouns I will get back mind, truth, wisdom, thoughts, things, and so on. If I say I want rather to have synonymous nouns, I get back Plato, Aristotle, philosophers, and so on. And that is basically, to some degree, you can actually do computation with the terms using features like that. So, for example, Jaguar minus Porsche equals Tiger. Yeah? So that can actually be computed. And not just for the main meanings of the words, but for all the meanings that have actually been trained.
Francisco, I just need to push on time. Francisco told me that he could speak for hours, and it's quite fascinating, and I agree, it's really fascinating.
Just 3 more slides. That is one of the main applications, of course, is to search. So if I can convert any piece of text into a fingerprint, I can, of course, use it to search. Using all the detailed features I have in my representation. So this is a real semantic search. If you want, you can find documents, for example, that don't use any of the search keywords you had in your query in the first place, because only fingerprints are compared. We can do classification, where a nice thing is we don't have to train the classifier. But here, like in this example, for example, we want to split animal names in mammals and non-mammals. The classifier is just generated by taking literally the word mammal, converting it into a fingerprint, and then comparing it to all the animal names. We can extract the semantically most important terms in any text, so creating useful short descriptions of news, for example, of documents in search results. It's better than just showing the first sentence or first 2 sentences. And we can semantically slice text into little paragraphs that contain a major topic. And with all of this, we end up with a system that shows certain advantages over the disadvantages I have described in the beginning. It's very simple. We have one algorithm, we have one operator, and one data format. Everything is decomposed in analogies. We have a very straightforward way of modeling the semantics by just ingesting in an unsupervised manner any collection of topical data. It's very efficient, so everything is represented using binary numbers. We actually don't need any GPUs or accelerators. A typical processor is able to do many millions of those comparisons per second. And it's very robust, which is practically speaking one of the main aspects to become used in a business context. Okay, so
thanks.
That's how far
Thank you very much. Thank you.
Thank you.
Please. Very inspiring, Francisco. Thank you very much. Very, very interesting. Not going to go too much into the techniques behind it, but I have a question around the usage, the business case. So, do you intend to develop yourself a full end-to-end solutions using your technology, or do you want to provide that as an API so other startups, other solutions providers can use your technology to develop vertical solutions?
Yeah, so we do have, in fact, an API, which was our initial business model. But when we started, nobody knew us, so nobody actually came to look for the new technology. So we decided to have an alternative first step, which was to offer this to the big enterprises. And that's sort of became a sort of self-fulfilling situation. We now have maybe a dozen customers worldwide, and each of them are sort of big enterprises beyond 100,000.
But on which business case, more specifically?
Yeah, so initially we had some fantasies on where this could be used, but in the end, customers came with very precise use cases themselves. So first we were sort of discovered by the financial industry with tasks like email compliance monitoring, with Know Your Customer projects, with analyzing social media data, clustering, finding out the topics, what are people talking about my product and my company. After all, we reached a use case that becomes sort of a killer app, which is contract intelligence. That's just as an example why basically if you as a provider of a technology, you imagine what your technology will be used for, you basically always are on the wrong page. Always keep waiting for your customer to tell you. And since we have started with the first large bank in working in the field, we have now like 5 or 6 banks just following this same pattern on contracts, on analyzing contracts, for example.
Okay, but ultimately the intent is to provide it as an API. I mean, it's right now you're just proving that it's working, but at the end what you would like is more work on an API model.
Absolutely. So technically speaking, it is an API. For practical reasons, we currently typically deploy the API at the customer side, but this is just for business reasons. And we plan to actually provide this as a public API, of course. Yeah.
Okay. Any question? Yeah, a lot of questions. Okay.
Hi. Thanks for the presentation. You mentioned at the beginning of the talk that it's quite difficult, or not to say impossible, to let's say investigate, solve bugs when you're using neural networks. I'm wondering where it's different in this case. I understand that because you have this kind of semantic representation in 2D of concepts, you can actually say, okay, I understand why this concept plus this concept leads to something. But the question is basically, how do you understand why a certain concept is represented that way?
Yeah, so it's a very good question that tackled us for quite a while. So we ended up with a standard procedure. So if we train, for example, on a new domain, so let's say we train a system to understand banking English, if I might call it like this. We ingest textbooks on investment banking, on banking rules. We ingest encyclopedias and stuff where concepts are defined properly. And we take, for example, to measure how well the system has picked up the semantics, we take dictionaries. Yeah? So a dictionary typically consists of a head word and a definition for the word. So by definition, if our system has properly picked up the meaning, the fingerprint of the head word and the fingerprint of the description should have a maximum possible overlap. If we don't see it having a sufficient overlap, it just tells us you have to provide more examples on the training. And because we can look on where sort of the biggest clusters are missing, we even know the topics of data that we have to capture and bring in. So that's one level, for example, of measuring how it does.
Other question? There was...
Hello. I'm wondering, when you analyze a contract, how do you cope with negatives? For example, cats and dogs are allowed, or cats and dogs are not allowed. Must look very similar to your system, but they are opposite.
They are nearly the same. So the typical answer I give to this question is dog bites man and man bites dog basically ends up being the same fingerprint. And that's, I don't want to say on purpose, but it's intentional, because the only thing we want to express with a fingerprint is that a certain sentence is about man, about dogs, and about biting. And that might seem incomplete, but in fact it's crucial for most of the practical problems. So in contract intelligence, for example, where we use the fingerprinting capabilities is that, for example, when the system is sort of trained interactively with a subject matter expert, the person selects an example sentence in an example contract where you find this is due 2 weeks after New Year. So we take this example, and by fingerprinting all the terms that are involved in the example, we figure out that 2 is a number, that weeks is some amount of time, that New Year is a particularly named date that you have. And what the system is able to do is by calling the similar terms, as I have shown in the primitives, it knows that 2, 3, 4, and so on are all numbers. It knows that weeks are like months, like days, like years. It knows that New Year is like Easter and President's Day and whatever. And what it does, it generates the combination of all the possible patterns it can extract semantically and generate some thousands of rules. Because we know that rules are always precise, and that's what we need when we work with contracts. And instead of having people explicitly define all the rules, we have the semantic expansion that actually does this automatically. And that's how we achieve very high degree of accuracy with very little effort. So like having 2, 3 people work on a dozen of contracts leaves you with some 80–90% of precision in the final extraction.
Okay, last question. I'm sorry, there's one there, and then we have to move on. But Francisco will be available after.
Yeah. How are you dealing with homonyms, especially when building the fingerprints?
I didn't understand with.
How are you dealing with homonyms? Words that are different.
We don't need to do anything specific to basically absorb the semantics. Homonyms are just words that share a lot of context. Yeah? So they appear in very similar contexts, which sort of systematically they end up having even very similar fingerprints. Yeah? That's basically the same approach that we humans have. If we hear a word very often in same contexts, we end up intuitively understanding that they are homonyms, for example. Yeah.
Okay, Francisco, thanks again. Very interesting, and it will be there if you have more questions.